Welcome to Modeling Mastery, the podcast where we explore the art and science of software design. I'm Hex.
And I'm Byte. In our last chapter, we focused on factories, the pattern that ensures our complex aggregates are born into a valid and consistent state.
We've handled the creation. Now, in Chapter 12, Repositories, we must address the rest of the aggregates lifecycle. How do we store them? How do we find them again? And how do we remove them?
And crucially, how do we do all of that without leaking persistence-specific details like SQL or JPA annotations into our pure, beautiful domain model? This chapter introduces the repository pattern as the essential abstraction that makes this separation possible.
It's the gateway between our domain and the database, and it's a fundamental part of a clean, decoupled architecture.
Let's get into it.
So, Byte, we've done all this hard work. We have our aggregates with protected boundaries, our factories create them in a valid state, and now we have this fully formed product aggregate sitting in memory. What do we do with it? We need to save it to the database. But our domain model is supposed to be pure. We can't just put an @entity annotation from Spring Data on our aggregate root, can we?
We could, but that's the path of coupling our domain model directly to our persistence framework. It's a pragmatic trade-off many teams make, but it's not the pure DDD or hexagonal architecture approach. In a truly clean architecture, our domain model, the hexagon, should have zero knowledge of the outside world. It shouldn't know if it's being saved to a SQL database, a NoSQL document store, or a simple file.
So how do we bridge that gap? We need a port in the hexagonal sense.
Exactly. And in DDD, that port is called a repository. The repository is a pattern that provides a collection-like interface for managing the lifecycle of our aggregates. This is the key metaphor the book gives us, and it's a powerful one.
What does collection-like interface mean in practice?
It means we design an interface that pretends all of our aggregates are just living in a giant in-memory map or set. This interface, which we define inside our domain model, would have simple, clear methods like add product, remove product, and product of ID. NID.
So from the perspective of our domain, it just looks like we're adding a product to a list.
Precisely. It's a beautiful illusion. The application service can use this interface to fetch an aggregate, call a business method on it, and then add it back to the collection to be saved. The domain model remains completely pure, dealing only with this simple, abstract collection.
But it is an illusion. Somewhere, something has to actually write the SQL.
And that's the adapter in our hexagonal architecture. In a separate infrastructure project or module, we write a concrete implementation of that interface, maybe called Postgres Product Repository. This class is where all the messy technical details live. It will use a JDBC template or a Spring Data JPA repository or a Mongo template. It will handle database connections, map result sets to objects, and translate our domain calls into database queries.
This is a good time to ask the question that confuses so many developers. How is this different from a DAO, a data access object?
It's a critical distinction. A DAO is typically a data-centric pattern. You'll often have a DAO for every table in your database, a product DAO, a task DAO, a discussion DAO. Its job is to perform simple CRUD operations on that one table.
But we've learned that our aggregates are not just one table. A backlog item aggregate is a whole cluster of objects. The backlog item root, its internal task entities, its discussion entity, and so on.
And that's the difference. A repository is domain-centric. Its job is to manage the lifecycle of the entire aggregate as a single atomic unit. When you call backlog item repository.add, that implementation is responsible for persisting the backlog item, all its tasks, and its discussion in a single transaction. This is why the book gives us the strict rule: you only define a repository for an aggregate root.
Because if you had a task repository, you'd be giving developers a backdoor to load an individual task without loading its parent backlog item root.
And in doing so, you'd completely bypass all the business rules and invariants that the aggregate root is there to protect. The repository pattern reinforces the aggregate boundary by ensuring that the only way to get a reference to any part of an aggregate is to ask the repository for the root. It's the only one with a key to the front door. So, Hex, We've defined this beautiful, pure product repository interface inside our domain model. It's got simple methods like add product product and product of ID, product ID, but this is just an interface. It doesn't do anything. Where does the actual database code live?
This is the essence of the dependency inversion principle and a cornerstone of hexagonal architecture. Our domain model, the hexagon, defines the port. That's the product repository interface. The implementation, the adapter, lives entirely outside the domain in the infrastructure layer.
For a developer using Spring Boot, this means in your infrastructure package, you'd create a class like Postgres product repository that implements product repository. This implementation class is where you'd inject your Spring Data JPA repository, or your JDBC template, or whatever persistence tool you're using.
And it's critical to understand that JPA repository is not your domain repository. It is a data-centric tool that your domain-centric repository delegates to. Your product of ID method, for example, would call the JPA repository's find by ID method and then translate the resulting JPA entity into your pure product aggregate.
This is where we hit the first major point of friction that the book discusses. The collection-like metaphor is an illusion, and it's a leaky one. In a real Java set, if I add product, it's in the set. If I get that product, change its name, it's just changed. I don't have to add it again.
But persistence doesn't work that way. There is a fundamental difference between an insert statement for a new object and an update statement for an existing one. How does our simple add product method know which one to do?
This is where modern ORMs like Hibernate and JPA try to be helpful with a pattern called a unit of work, which Spring manages for us as the persistence context. When you're inside a transactional method, you use your product repository to find a product. That product instance is now managed by the ORM.
What does managed really mean here?
It means the ORM has a snapshot of its original state. When your application service calls a business method like product.changeName to new name, the product state in memory is now different from the snapshot. You don't even have to call a save method. When your transactional method finishes, the ORM sees the difference, automatically generates an update statement, and flushes it to the database.
This is the magic of modern ORMs. It makes the persistence implicit. The developer just changes the object, and the ORM tracks the changes. The book points out that this is incredibly powerful, but also a source of confusion. It can be non-obvious that a simple method call will result in a database write.
And this is why many teams, as the book advocates, decide to make their persistence more explicit. They might choose to break the pure collection metaphor in favor of clarity. Instead of just add product, their repository interface might have two distinct methods: add product for a new aggregate, which clearly maps to an insert, and save product or update product for an existing aggregate, which maps to update.
It's a pragmatic trade-off. You sacrifice the purity of the collection illusion for the clarity of an explicit command. The goal of the repository is to abstract the how of persistence, but it's often wise not to abstract the that of persistence.
Exactly. So the typical flow in a Spring application becomes a clear process. The application service method begins, which also starts the transactional context. Then inside that method, the service uses the product repository to find an aggregate. After that, it calls a business method on the aggregate root. And finally, to make the save clear, it explicitly calls product repository.saveProduct to signal its intent. The implementation underneath then uses the ORM to flush those changes. This way, the act of saving is a clear, deliberate step in the use case.
We've spent a lot of time on how repositories help us write data, how they save and update our aggregates. But what about the other side of the coin, reading data?
This is a massive pain point I see on Teams, Hex. A developer needs to populate a complex dashboard, a list of 100 products with the product owner's name and the current sprint's name. Their first instinct is to use the product repository.
And what happens when they do that?
It's a disaster. Their code looks something like product repository.findAll. This loads 100 full product aggregates into memory. But the product only has the owner ID and sprint ID because We correctly followed the rule of referencing other aggregates by identity.
So now they have a classic N+1 query problem.
Exactly. They're forced to loop inside the service for each product, get the owner ID, call the user repository, get the sprint ID, call the sprint repository. It's incredibly slow and inefficient. Worse, from a domain perspective, they're loading the entire complex aggregate with all its internal state and behavior when all they needed was 3 strings of text for a UI. It's like buying an entire factory just to use 1 screwdriver.
And the other anti-pattern is just as bad. To fix the N+1 problem, they start polluting the product repository interface. They add methods like find products with sprint and owner names. Now the domain repository is coupled to a specific UI use case, and its implementation is a horrible, complex JPA query.
This is where the book makes a critical clarification, and it's a huge aha moment for many developers. The repository pattern is optimized for transactional consistency, not for query performance. Its primary job is to get one aggregate by its ID so you can call a business method on it. It is not a general-purpose query tool.
This insight is what leads directly to a CQRS, Command Query Responsibility Segregation mindset. The book strongly advocates for separating your write model, which consists of commands, aggregates, and repositories, from your read model, which consists of queries.
In practical terms, this means it is perfectly acceptable and, in fact, encouraged to have a completely separate, thinner data access mechanism for your read-only queries.
For me as a Spring developer, this is a huge relief. It means my product repository stays clean and simple with just add, save, and product of ID. But for that dashboard, I'll create a separate product query service. This service won't even use the domain model. It will inject a JDBC template or maybe a read-only JPA repository configured to use a DTO projection.
And with that, I can run a custom optimized SQL query that joins the product, team, and sprint tables and maps the result directly into a flat product dashboard DTO. That DTO is just a simple, dumb data container that perfectly matches what the UI needs. The query is fast, efficient, and it completely bypasses the aggregate model, which is fine because we're not running any business rules. We're just reading.
This brings up another huge benefit of the repository interface. Because it's an abstraction, a port in hexagonal architecture, we can have multiple implementations. In our production code, we have our Postgres product repository that talks to the real database. But what about our unit tests?
This is the best part. In my unit test for my application service, I don't want to spin up a real database. That would be a slow integration test. So I just create an in-memory product repository that implements the same product repository interface. Its implementation is just a simple handshake map that stores the product aggregates.
So you can test all of your application logic, your port, completely in memory, and it's blazing fast.
Exactly. I can test that my service calls the product of ID method, then calls the business logic on the product, and then calls the save method, all without ever touching a disk.
So the repository pattern gives us 2 powerful forms of separation. It separates the domain from the persistence implementation, and it forces us to think about separating our command write logic from our query read logic. It's the key to a clean and performant persistence layer.
We've covered a lot of ground in this chapter on repositories. We've defined them as a collection-like illusion, a port in our hexagonal architecture. We've discussed the practical challenges of implementing them with modern ORMs and the critical importance of separating them from our read-only queries.
To wrap it up, let's look at the repository's role in the complete lifecycle of an aggregate, starting from the very beginning, with creation.
In our last chapter, we discussed factories. We established that an application service would call a product factory to create a new product aggregate. The factory does its job, enforces its creation time invariance, and hands a brand new, valid product instance back to the application service.
And what does the application service do with this new instance?
It immediately hands it to the product repository's add method. This is the first time the repository sees this aggregate. Its implementation is responsible for taking this object and performing the initial atomic insert of the entire aggregate cluster, the product root, its internal task objects, and so on.
So the factory creates, and the repository adds it to the collection.
Precisely. Now, fast forward. A week later, a user wants to change the name of that product. A new use case begins. The application service is called. Its first step is to go to the product repository and call product of ID to fetch the existing aggregate.
And this is where the repository performs reconstitution. Its implementation queries the database, pulling all the necessary data from multiple tables, and carefully rebuilds the entire product aggregate, its root and all its internal parts into a single, consistent object in memory.
So the application service now has this fully formed aggregate. It then calls the business method on the root, like product.changeName. The aggregate root enforces its invariance, and the state in memory is changed.
Finally, the application service needs to commit this change. It takes the modified product aggregate and hands it back to the repository, calling the save method.
And the repository's implementation now performs its second major job. It takes this modified cluster and persists the changes. This might be an automatic update tracked by a unit of work or an explicit one. But crucially, it persists the entire aggregate's changes within a single transaction, ensuring the consistency boundary is always maintained.
So the repository handles the add, the find, and the save. It's the complete persistence gateway for the aggregate root.
And this is why the book states that the repository is one of the most important clients of the tactical patterns we've discussed. The repository's implementation is where the design of your aggregates, entities, and value objects meets the harsh reality of a database.
If you've designed your aggregates to be small, your repository implementation will be simple and fast. If you've created a giant aggregate, your repository will be a complex, slow monster that has to load and save a massive graph of objects.
Your repository's performance and complexity are a direct reflection of your aggregate design skills. And that brings our entire tactical design journey to a close. We started with the smallest building blocks, entities and value objects. We grouped them into aggregates. We gave them behavior with domain services. We announced their changes with domain events. We organized them with modules. We created them with factories. And now we've persisted them with repositories.
That's the complete tactical toolkit. These are the patterns that allow us to build a rich, expressive, and robust domain model that is cleanly separated from infrastructure concerns.
Exactly. And with these tools in hand, we're ready to move on to the final part of the book, where we'll see how these patterns are applied in different architectural contexts, from REST and SOA to full-blown event sourcing.